Welcome everybody. We've been given f of x is equal to limit n tending to infinity n raised to the multiplied with x positive n times x positive n over 2 multiplied, and it goes on all the way to x positive n over n. Now this is in turn divided by n factorial times x squared positive n squared product multiplied with x squared positive n squared over 4. It goes all the way to x squared positive n squared over n squared. This entire component is raised to the power of x over n. Now we are given 4 choices. First one is f of 1 over 2 is greater than, this is A, and B is f of 1 over 3 is less than equal to f of 2 over 3, and C is f of 2 is less than equal to 0, and D is f dash of 3 over f of 3 is greater than equal to f dash of 2 over f of 2. Now more than one choice can be correct, so you can have a look at it and take your time, and when we return we will see the solution. Okay, foremost what we are going to do is we are going to consider the given question. So we got f of x is equal to limit n tending to infinity. Now if you observe this question, this is n, actually n is resting over 1, and you have n over 2, and the next term is going to be n over 3, and so on and so forth. So what we are going to do is we are going to take this n out. So I'm going to write this as n raised to the power of n. Taking n out, actually I'm going to take n over 1 out. That would give me the first term to be x over n positive 1. The second term, for the second term I'm going to take n over 2 out. So let me place n over 2 over here. There's no space there, so if I take n over 2 out, this is going to be 2 times x over n positive 1. And for the next term I'm going to take n over 3 out. This is going to be 3x over n positive 1, and so on and so forth. For the final term I'm going to take n over n out, and that is going to give me n times x divided by n positive 1. Okay, so this is divided by, from here I'm going to take, this is actually resting over 1 squared, okay, because this is 2 squared and the next term is 3 squared. This is given to be as n squared, so that is the way the terms are arranged. So let me take n squared over 1 squared out. So over here you have n factorial. I'm going to take n squared over 1 squared out. So that is going to give me x squared divided by n squared positive 1. For the next term I'm going to take n squared over 2 squared out. So n squared over 2 squared out goes off. So this is going to be 2 squared x squared divided by n squared positive 1, and for the last term I'm going to take n squared over n squared out, and that is going to give me n squared x squared divided by n squared positive 1. Okay, so this entire component is raised to the power of x over n. Fair enough, right? So now what we are going to do is, you see here this is actually n times n times n times all the way up to n. Okay, so over here we have n raised to the power of n. This is n multiplied with n times, so it is going to give us n raised to the power of n, right? Now for the denominator, for this denominator I'm talking about, you have 1 here, and then you have 2 times, then 3 times, and all the way n, right? So that's going to be 1 into 2 into 3 etc. n. So what is this? This is nothing but n factorial. So place that n factorial there, and this is multiplied with 1 positive, I'm going to write it as x over n, times 1 positive 2x over n, times 1 positive 3x over n, etc. etc. all the way to 1 positive nx over n. So this is for the numerator, divided by the denominator. You see you have n squared times n squared times n squared all the way up to n terms. So this is how it is written, n squared times n squared times n squared all the way up to n terms, and that is raised to the power of 2. So n squared is multiplied n times, so n squared raised to the power of n, right, which is nothing but n raised to the power of 2n, right? So you have n factorial times n raised to the power of 2n. Over here you have 1 squared times 2 squared times 3 squared. So what is that? If I were to multiply 1 squared times 2 squared times 3 squared etc. all the way to n squared. So can I write this as n factorial raised to the power of 2? That's exactly what I'm going to do. So this is the quantity present in the denominator. So it's going to be n factorial raised to the power of 2. And this term I'm going to write it as 1 positive x squared over n squared multiplied with 1 positive, this is 2 squared over n squared times x squared, and this is 1 positive 3 squared over n squared times x squared all the way to 1 positive, this is n squared over n squared times x squared. Okay, this entire component is raised to the power of x over n. This is what we have got. Now of course you have a limit n tending to infinity. Now you can flip this and rewrite the terms. N raised to the power of n times n raised to the power of n is going to be n raised to the power of 2n. This n factorial will join this. This will be flipped and it will go to the numerator, n factorial raised to the power of 2, and multiplied with 1 positive x over n times 1 positive 2 over n times x times 1 positive 3 over n times x etc. up to 1 positive n over n times x, divided by, for this we got, as I mentioned to you, this is going to come to the denominator. So you have n factorial multiplied with n factorial, right, and we have this 2n there, so you need to multiply that n raised to the power of 2n times 1 positive x over n. Okay, so I'm going to write it as 1 over n squared times x squared multiplied with 1 positive, this is going to be 2 over n squared times x squared times 1 positive 3 over n squared times x squared all the way to 1 positive n over n squared times x squared. Don't cancel anything, just retain it as it is. Okay, so you have a parenthesis there, and the whole parenthesis, this is entirely raised to the power of x over n, and you have limit n tending to infinity, and this quantity is going to be f of x. Now clearly n factorial squared and these two n factorials get cancelled. N raised to the power of 2 and n raised to the power of 2n gets cancelled. Now what we are going to do is we will have to take ln on both sides, or I would say just take ln. So taking ln both sides, we get, so what do you get? You get here ln of f of x. Now the limit and the ln can be interchanged, so this can be rewritten as limit n tending to infinity ln of 1 positive x over n multiplied with 1 positive 2 over n. In fact, we can have written it as 1 over n times x. So anyway, 1 positive 2 over n times x times 1 positive 3 over n times x, etc. 1 positive n over n times x. So this is for the numerator. This entire component is divided by, of course, the parenthesis will flow all through. Okay, so this is going to be 1 positive 1 over n the whole squared times x squared multiplied with 1 positive 2 over n the whole squared times x squared times 1 positive 3 over n the whole squared times x squared, etc. 1 positive n over n squared times x squared, and you have the parenthesis there. Okay, x squared and parenthesis. So this is raised to the power of x over n. Now we know a formula, right? So ln a raised to the power of b is going to be b times ln a. So with this formula I can bring this x over n over here, right? This can be brought. So let me move to the next space. So we have another formula of ln of ab is nothing but ln a plus ln b. We can use this formula, right? So by that formula I can actually, and we can also use this formula, ln of a over b is equal to ln of a negative ln of b. So these two components, ln a over ln b, I want to rewrite this as limit n tending to infinity x over n. So this is going to be ln of 1 positive x over n times 1 positive 2 over n times x times 1 positive 3 over n times x, etc. 1 positive n over n times x. This is the first ln minus ln of 1 positive 1 over n squared times x squared times 1 positive 2 over n the whole square times x squared, etc. times 1 positive n over n squared times x squared, right? So you place the parenthesis. Now we will employ this formula. So this is equal to limit n tending to infinity x over n. So ln of 1 positive x over n plus ln of 1 positive 2 over n times x plus, etc. plus ln of 1 positive n over n times x. So this is the first ln, okay, minus this ln. So this is going to be ln of 1 positive 1 over n the whole square times x squared plus ln of 1 positive 2 over n the whole square times x squared plus, etc. plus 1 positive n over n the whole square times x squared. Okay, so this minus this is what we have got. Of course this x over n goes all through. Having got this, now what I wish to do is I would like to rewrite this as a sum. So limit n tending to infinity of x over n. I want to write this as sigma. Now this is actually 1 over n, 2 over n, 3 over n. So I'm going to write this as ln of 1 positive r over n, right, where r is ranging from 1 to n. Okay, fair enough, right? And you have x there, so you place that x, and followed by sigma. Similarly, this is going to be ln of 1 positive r over n the whole square times x squared. R is ranging from 1 to n. Okay, so this is what we have got. Now there is something that you will have to know. This is a very important concept. Now I have introduced r over n. So r over n is the discrete sample point. Okay, that is used to approximate the behavior of the function over a continuous interval. So what do? We put r over n to be equal to y. Okay, so this will represent the transformation from a discrete set of points, because we already defined that r over n, alright, from a discrete set of points to a continuous variable y. That varies continuously over the interval 0, 1. Okay, so this is as n is tending to infinity. Now, why am I explaining you all these things? Because we will be utilizing the Riemann's integral to convert the sum to the integral. Okay, so this is actually converted to using the Riemann's integral. Right, so this is of the form. Let me write this, represent this in the Riemann's integral requirement. So x over n, what I'm going to do, I'm going to write it like this: x times the limit n tends to infinity of 1 over n sigma r is equal to 1 to n ln of 1 positive. Now r over n, when we place the integral, we will have to replace it with y. So r over n times x followed by negative x, limit n tends to infinity of 1 over n sigma ln of 1 positive r over n squared times x squared. Okay, r is equal to 1 to n. Because x is totally independent of the count of the running variable, so we don't need to include it in the sum. So this representation is rewritten as x times integral 0 to 1 ln of 1 positive, this is y times x and multiplied with dy, followed by negative x 0 to 1 ln of 1 positive x squared y squared multiplied by dy. Okay, so this is the famous Riemann integral equivalence, where the sum is converted to the integral. So this is the important concept. So this definition which I have given you is what converts this integral. Okay, so directly we cannot make the conversion. On the left we have ln of f of x. Okay, this is what we have got. So now we will have to integrate this. So how are we going to integrate this? Let's see that. So what we are going to do is we are going to take, let xy be equal to t. X is treated as a constant. You differentiate y, you get dy is equal to dt. So over here, you see x and dy, they can be clubbed. So this is going to be ln f of x is equal to integral ln of 1 positive t times dt. Now when y is equal to 0, t is equal to 0. When y is equal to 1, t is equal to x. So the limits are 0 to x for this quantity. For the second quantity, we don't have to do anything, just the same substitution remains. So it's going to be integral 0 to x ln of 1 positive t squared times dt. Okay, so this is what remains. So now we will have to integrate this. Now if you see the requirement of the choices, at one place we are talking about f dash. So we need to bring in the differentiation. So differentiating both sides, we get, so what do you get? Differentiation of ln of f of x is 1 over f of x times the differentiation of fx is going to be f dash of x. And when you differentiate this, you will have ln, in place of this variable, running variable, you substitute x and then you differentiate x, so you get 1 there, okay, followed by negative. In this case is going to be ln of 1 positive x squared. Differentiation of this x will give you 1. So this is how we do the differentiation part. So this on the left hand side is going to be f dash of x over f of x. Now as I mentioned to you, this can be rewritten as ln of 1 positive x over 1 positive x squared, right? So this is already got. Now we will have to look into certain values, certain choices. Now let us check for choice number D. Okay, choice number D states f dash of 3 divided by f of 3 is greater than or equal to f dash of 2 divided by f of 2. So we will have to check for x is equal to 2. So what happens when x is equal to 2? You get f dash of 2 divided by f of 2 is equal to ln of 3 divided by 2 squared is 4. So 4 added with 1 is 5. So this is going to be ln 0.6. So when x is equal to 3, this is f dash of 3 divided by f of 3 is equal to ln of 4 squared is this is 3 squared. So 3 positive 1 is 4, 3 squared is 9, 9 positive 1 is 10. So this is 2 over 5. So that means this is ln of 0.4. So now we have to check between ln of 0.6 and ln of 0.4. Now for this, you go to the graph of ln. Now this is 0 to 1. Between 0 to 1, the graph is increasing. Now 0.4 is here and 0.6 is here. So between this, which one do you think is a greater term? Between left and right, you tell me. So clearly 0.6 is way above than 0.4, right? So this is going to be greater. But what is 0.6? 0.6 is when x is equal to 2. When x is equal to 2, you get ln, or I would say f dash of 2 divided by f of 2 is greater than or equal to f dash of 3 divided by f of 3, right? So because all from this graph, ln x graph. So this cannot be. We have to drop d. So we drop d out. D is dropped. So next comes f of 1 over 3 and 2 over 3. Okay, let us check that. Now we will have to look into this one. F of 3 less than or equal to f of 2 over 3. Now we are interested in x being in the interval 0 to 1. So clearly x will be greater than x squared and x positive 1 will be greater than x squared positive 1. So this in turn would mean x positive 1 divided by x squared positive 1 would be greater than 1. So this component is greater than 1. So let us go back to the actual ln. Suppose I were to take a ln of this, because we started with or we have this f dash of x divided by f of x, which is equal to ln of 1 positive x divided by 1 positive x squared, right? So because of the fact that x positive 1 over x squared positive 1 is greater than 1, this is going to be positive, right? So that would mean we are looking at increasing function. So this means f dash of x is increasing. This means f of x is increasing for x in the interval 0 to 1. So that means, you see here, f of 1 over 3 less than or equal to f of 2 over 3. This is going to be true, right? So if this is true, obviously this cannot be true. Okay, so we have handled the 3 choices. What remains here is the last one. So let me go back to the last one for f of 2. Okay, so I need a new sheet of paper. I think I can use this information for deciding on this question. Okay, so clearly from here, f dash of 2 divided by f of 2 is equal to ln 0.6. So f dash of 2 divided by f of 2 is equal to, what is that, ln 0.6. Now what is ln 0.6? Ln 0.6, where is that graph we had? Okay, ln 0.6 is actually negative, so have that in mind. Now, this would mean f dash of 2 is equal to f of 2 times ln 0.6. This means f dash of 2 is decreasing, right? So, this in turn would mean our f of 2 is decreasing, right? So outrightly from here we can state that f of 2 is less than or equal to 0. So this in turn would mean this choice is correct. So this completes the solution to the question. So finally, to wrap it up, the choices are B and C for this beautiful question. So please like, share and subscribe. Thank you everybody.